Chris Umgao of Notre Dame, who will speak about the coisotropicity of fixed points and the torus action on the variety of Lagrangian subalgebras.
Okay, thank you for introduction. Thank you, organizers, and thank you for having me here. In my talk, I will introduce my recent work on the topic of coisotropicity of fixed points and their torus action on the variety of Lagrangian subalgebras, which is the recent work in my PhD thesis. How does it work? All right.
Go ahead.
Oh, okay.
Sorry.
So the problem of coisotropic subalgebras is a problem initiated in the work of Marco Zambon, and my work is related to the theory of semi-simple Lie algebras and algebra geometric methods, including linear algebraic groups and toric varieties. Oh, sorry. So to begin with, let G be a semi-simple Lie algebra over complex number field with adjoint algebraic group capital G. Let H be a fixed maximal torus of G and B be the Borel subgroup of G that contains H. So we can determine a set of simple roots, which is called gamma. Let M be the derived group of B, which is the unipotent radical of B. And we use the German letters, we use the Fraktur letters HBN to denote the Lie algebras of capital HBN respectively. With that basic settings, let's recall what is a Manin triple. A Manin triple consists of a Drinfeld double on which there is an undegenerate invariant bilinear form, which is defined in the following way. And G diagonal and GST star are maximal isotropic subalgebras of G plus G, which is defined as diagonal line and this one. Okay. So this is a Manin triple, and from the Manin triple we can introduce the bialgebra structure on this one, on G diagonal. If we identify G with G diagonal and G star with GST star defined above, then this is the Lie algebra G is a Lie bialgebra, and G is and its Lie group G is a Poisson Lie group. And here comes the definition of Lagrangian subalgebras. A Lie subalgebra of G plus G is called Lagrangian if its dimension is equal to dimension of G, which is half of the double. In addition, L is an isotropic subspace of G plus G with respect to the inner product defined above. We use the symbol L of G plus G to denote the set of Lagrangian subalgebras of G plus G. For simplicity, we just call it simply as L. Since being subalgebras and being isotropic are polynomial conditions, so firstly, notice that this is a subset inside the Grassmannian. Since these conditions are algebraic conditions, so the variety L is an algebraic subset in Grassmannian. We call this algebraic closed set the variety of Lagrangian subalgebras of G plus G. So here, the term variety doesn't mean that it's irreducible. It can be reducible, and in general, it is reducible. It has many components. And the fact is that the double group G cross G acts on this variety via the natural adjoint action. So here are some basic examples in case you forgot bilinear form, I rewrite it here. So basic examples are like G diagonal, G anti-diagonal, and G ST star. And there is a more complicated example, which is the zeta s. And the notation NS and NS minus here will be introduced later. And since G cross G acts on this variety, so any G cross G translation of the aboves are Lagrangian subalgebras. And then we can define, it's the point to define coisotropic subalgebras. Since G is a Lie bialgebra, so its dual is again a Lie algebra. A subalgebra M of G is called coisotropic if its annihilator inside G star is a subalgebra in G star. And the annihilator just means all of the linear functionals on G which vanish on the subalgebra M. And a fact is that one can embed a coisotropic subalgebra one can relate Lagrangian subalgebra with a coisotropic subalgebra in the following way. So suppose that M is a coisotropic subalgebra. We use M perp as the counterpart of M naught, which is the annihilator in G star. And one can check that this direct sum is a Lagrangian subalgebra of G plus G. So start from coisotropic subalgebra M, one can form a Lagrangian subalgebra, which is M diagonal plus M perp. And we call a Lagrangian subalgebra L coisotropic if L comes from this way. And let's give this set a name. So it's called CL of G plus G. Let's just call it CL. So it consists all of the coisotropic Lagrangian subalgebras. So in other words, so this is just from the definition. A Lagrangian subalgebra is inside that set if it has the following form. And in fact, this is a subvariety. One fact that may be interesting to Poisson geometers is that there is a Poisson structure pi L on the variety L. And moreover, if L is coisotropic, then the Poisson structure vanishes on coisotropic points. And there is a torus action. The torus is there is a torus action on this variety, and the torus is the diagonal line of H inside G cross G, where H is the where H is fixed maximal torus of G. Okay. So far, let me write a brief summary here. So we've defined the variety of Lagrangian subalgebras. Which is a subvariety of Grassmannian. And CL is a subvariety of Lagrangian subalgebras. And my target is to determine coisotropic subalgebras of G plus G, but it seems a little bit hard to do it. Instead, I study the torus fixed points on the variety. So So there is a torus action on this variety. What I want to study is the fixed points of this torus action. And in fact, this is equal to torus fixed points in the variety of Lagrangian subalgebras intersect with CL of G plus G. So that means to study this set, I can firstly look at the H diagonal fixed points inside this variety. And this variety is already clear in a research paper by Sam Evans and Jianghua Lu. And then inside this torus fixed point set, I can check their coisotropicity. That's my strategy. In particular, in this talk, I want to focus on one of the irreducible components inside the variety of Lagrangian subalgebras, which is called G bar. So this is defined as the G cross G orbit through the Lagrangian subalgebra G diagonal taking closure. And you can check that the stabilizer at G diagonal, this is equal to G diagonal. So this orbit is just isomorphic to G cross G modulo G diagonal. And this is isomorphic to G. So you can regard this orbit as a copy of G inside this variety. And its closure is called the wonderful compactification. And in the following, I will give the torus fixed points inside that irreducible components and decide and determine which of them are coisotropic. And it turns out that this fixed point set is a union of toric varieties, and we can describe them. Using combinatorics of Well group. So here are some more notations. Let zeta naught be the Lagrangian subalgebra H diagonal plus n minus. And to study this fixed point set, to study a variety, one wants to decompose it into irreducible components. So let the union of xi to be the irreducible decomposition. Since this variety is smooth, this is due to a result by Iverson. The irreducible components of this fixed point set are connected components, and hence this is a disjoint union. And I can show that each irreducible component xi contains some point of the form like yw x on zeta naught, where y and w are Well group elements. And I denote xyw to be the irreducible component that contains such a point. So that means this is the irreducible decomposition of the torus fixed point set, which is a union of xyws. So to study this variety, it suffices to study all of the xyws. If I can describe them clearly, then this variety is clear. And here are some more notations. Recall that gamma means the set of simple roots. And for a subset inside simple roots, let PS be the corresponding standard parabolic subalgebra. And here is the Levy decomposition, and NS be the opposite H stable new radical. And GS is the MS here is reductive, and GS is the derived algebra, which is semi-simple. And with the corresponding adjoint group GS. With the above definitions, we can define what is zeta S here. So this is a Lagrangian subalgebra. And I define the variety KIs to be the closure of H cross H orbit through the zeta S. And then I can show that this is a toric variety for the torus HS, which is a maximal torus inside GIs. And here are some more notations. Before continuing, let's give a quick review on what is a toric variety. So a toric variety, X is a normal variety that contains a torus T as a dense open subset, together with an action map, which extends the natural action of T on itself. And roughly speaking, a fan in Rn is a collection of columns. And the fact is that a toric variety is completely determined by its fan. So, and examples of toric variety include projective spaces. So let me draw a picture here. I would like to, what I want to do is to draw an example for P1. So this is R1 with origin. And the columns here, so this is a fan. The columns here are like the half spaces. So and this two fan has an intersection, which is just the origin. And the point is that on one side we have columns in the fan of X. And on the other side, so columns corresponds to affine open set in P1. This column corresponds to and this column corresponds to and their intersection corresponds to their intersection, which is the torus, which is the algebraic torus C cross. And this is C1. This is again C1. And what does it mean by their intersection? Intersection of columns is a common phase of both of the columns. What happened here is that this affine opens give an affine open cover for the projective space P1, and they grew up along this set. So two cones glue up with respect to their intersections. And in my situation, what I want to focus on, so the fan that's interesting to me is the fan determined by a well chamber. So let's draw a picture here. This is well chamber for SL2. There are 6 chambers in total, and each of these chambers corresponds to a well group element. And probably let's say this is the fundamental well chamber. And they will correspond to affine opens in my toric varieties. So let's just move forward. So firstly, I define the subvarieties sigma s, which plays the role like so this is an open affine in the toric variety Ks, which plays the role like fundamental well chamber here. And the structure of Ks is a toric variety, and its fan is given by the well chamber decomposition of GS, for which the well group is W sub S. And here, this is an affine open cover for the toric variety. And you see that these affine opens are labeled by the well group elements. They correspond to the well chambers. And in fact, the XYWs are translations of toric varieties. That's my result. So recall that this is irreducible component of the torus fixed points. And so far, what I've determined are the torus fixed points. And next thing to do is to determine their coisotropicity. And these are the part 2 of my main results. There exist coisotropic points in the irreducible component XYW if and only if the following conditions hold. And if the above conditions hold, then there are finitely many coisotropic points inside this irreducible component. Each one corresponds to a subset of IYW. And so that means coisotropic points in the torus fixed point set form a finite set. It's discrete. So here is a quick example. We look at the example 1G equal to SL2. So the corresponding adjoint group is PGL2, right? And we take the maximal torus to be the diagonal matrices, and E and F are like that. And here is a fact. The wonderful compactification G bar can be identified with the projectivized space of 2x2 matrices. And moreover, there exists a G cross G equivariant isomorphism from this space to G bar, which send the identity to the G diagonal. And it's easy to see that the H diagonal fixed points inside this space are diagonal matrices. Disjoint union is E and F. So back to the language of Lagrangian subalgebras. the H diagonal fixed points in G bar are given by these sets. Where S is the order 2 element in the well group of SL2. And for the first one, this is a toric variety. And it's a toric variety for the torus H. And the second one, third one are discrete points. They are toric varieties for trivial torus. And besides G bar, I also got results in other irreducible components. So G bar is just one irreducible component of. Okay, this is the last page. Okay. So I can apply a similar method to other irreducible components of the variety of Lagrangian subalgebras. And the result is that the H diagonal fixed points are product of toric varieties and a homogeneous space of a special orthogonal group. And among these fixed points, the coisotropic points along the toric variety factors are discrete. And that's all.
Time perhaps for one quick question. Anyone? Anyone on Zoom? I guess not. So thank you very much again.